So far, we have been looking at things which are part of classical cryptography rather than modern cryptography. Um, Today will be the last time we'll be looking at some concrete examples using methods of cryptography which were classically used for private cryptography rather than public key cryptography. And so from next time, we'll start from chapter 2 in the book. And I hope you will have read the section that I asked you to read in the last chapter, in the last video. But till then, so let me show you some other classical methods, and then we'll move on to chapter 2. So first of all, in Hill cipher for n-cross-n matrices. So last time, the example I gave, we were dealing with only one, only 2x2 matrix, and the Hill cipher, as mentioned, was going to deal encryption k of x is equal to mx. Now you can make this slightly better, where m is equal to n cross n matrix, and n and what do you call, and x is equal to a column vector of x1, x2 dot 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 xn. What you can do is actually combine this, can be combined with Wigner cipher, the standard Wigner cipher by letting the shift be by another column plus b, right? And in that case, the encryption is going to look like encryption k of x is equal to mx plus b, very much similar to an affine cipher. And then my x is a column x1 to xn, and b is a column b1 to bn, where you're shifting the first letter by b1 places, second letter by b2 places, and so on and so forth, nth letter by bn places. So last time we saw if the matrix was 2x2, how to invert. This time I'm going to show a general process to invert matrices, invert m cross m, sorry, to invert n cross n matrices, n cross n matrices, and the process goes as follows. So suppose m is equal to, example, suppose m is equal to, let's say, 1, 2, 3, 4, 5, 6, 7, 8, and 10, because I want things to be invertible, right? So I'm going to take this, and we are going to say n is equal to 26, so we are dealing with things mod 26. So everything is in Z26. Okay, so what we do is start by writing the matrix as 1, 2, 3, 4, 5, 6, 7, 8, 10, 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, And then the idea is you want to reduce the first three columns to this to what is in the second three columns. So you want to reduce the first three columns to 1 0 0 0 1 0 0 0 1, and whatever is on the right hand side is actually your inverse. So my first operation is row 2 is equal to row 2 minus 4 times row 1, which gives my, and row 3 is equal to row 3 minus 7 row 1. Okay? Which would, after subtraction, give me 1 2 3 1 0 0 0. Well, 4 times 2 is 8. 5 minus 8 is minus 3, but I'm dealing with Z26. So 26, so minus 3 is 25, 24, 23. So this is going to be 23. This is going to be 20. This is going to be 22, 1, 0. And 0, 20, 15, 19, 0, 1. Okay. Now, I don't like this 20 here. I would like to get rid of it. Multiply everything. R2 goes to R2 into 23 inverse, which is equal to 17 times R2. Okay, and so multiplying things by in the second row by 17, I get 1 2 3 1 0 0 0 1 2 10 17 0 0 20 15 19 0 1. Okay, next operations. R1 is equal to R1 minus 2R2, R2, and R3 is equal to R3 minus 20 R2. Okay, doing this gives me 1 0 25 7 18 0 0 1 2 10 17 0 0 0 1 1 24 1. Now for the finishing touches, we just have to do R1 is equal to R1 minus 25 R3, and R2 is equal to R2 minus 2 R1, which shall give me 1 0 0 0 1 0 0 0 1 8 16 1 8 21 24 1 24 1, and therefore my M inverse is then 8 16 1 8 21 24 1 24 1. So yes, I wrote this down really fast because I had done this computation before, but this is the way you can do these computations. Okay, and so here's a method where you are using higher degree matrices, and you can invert them via this method. Okay, so while on the exam and something, I won't give you this complicated a matrix. I might give you a matrix to invert which has much simpler terms. Okay, so make sure you're slightly familiar with these. I will also give you homework problems today that will get you familiar with certain things. There are two more types of ciphers that we would like to see. The first one is a transposition cipher. Transposition cipher. Okay. And what this cipher does is basically it is jumbling up the letters, so it is creating an anagram, except with a lot of garbage extra thrown in. Okay, so the way to do it is you take a key. So key, let us say assume a key is equal to BOMBE. Okay. Now it doesn't matter what exactly the numbers are for these letters. However, you just write them in alphabetical order. You count them in alphabetical order. So in alphabetical order, the first B comes first. We ignore, even if there are some letters appear twice, it's fine. The second is going to be this B, third is E, fourth is M, and fifth is 1. O. Okay? And so this gives us a permutation that we want. Okay? So gives us a permutation. Permutation 1, 5, 4, 2, 3. Okay? Now, let us say your message that you want to encrypt is plain text. Plain text is cryptography is fun. CRYPTOGRAPHY is fun. Okay, this is a long message. How do we encrypt this using cryptography? Using this method. And the idea is you write them down as columns, in columns using your permutation. You make as many columns as the length of your word. So L is equal to 5. Length L is equal to 5. So make 5 columns. Make L is equal to 5 columns. Okay. And you then start writing the message till it forms a perfect square. Okay. CRYPTOGRAPHY. Great. What now? Now you fill up the rest with garbage. Okay. So maybe I will write X, Y, Z. Great. And now these are just letters that you've used to fill up the alphabet. So I accidentally said perfect square. It just needs to be a rectangle. Okay, so these are called nulls. Nulls. And they're just used to fill and make it a perfect rectangle. Just used to make a rectangle. Okay. And now the idea is you read off columns, encryption, write message, write message in terms of columns in numerical order. Numerical order. So the first column is COHU. So my ciphertext is going to be ciphertext COHU. Second column is not RGYN. It is the one that is named 2. PASY TPFZ. 4 is YRIX RGYN. Okay, and so this is my message. And how do I decode it? Well, decryption. Knowing the key, write message into a rectangle, CT rectangle of L columns, and rearrange the columns according to the permutation that you know. And rearrange the columns according to the key. So if you first just write down the columns, it's going to look like it's going to read COHU PASY TPFZ YRIX RGYN. That would be the columns. But you know which column should come first, right? Because of the key that we have. Well, the only way you can decrypt is if you know the key. So knowing the key allows you to do that. Okay, so that's an example of a transposition cipher where you are just jumbling the letters of the message rather than everything, random letters, and adding some extra garbage so that it's not completely just the word missing. Another cipher that is often used, that is slightly different, is the bitwise shift cipher. Bitwise shift cipher. Now this cipher is slightly different than the other ciphers for 2 points. First, you work with alphabets of bytes rather than English letters. Work with alphabets of bytes rather than English letters. And second, because we are dealing with bytes, you use XOR instead of modular addition. Okay, so it is easy to see that the properties still hold. And oops, I hate things. Okay, so things are going to be done in hexadecimal code. Hexadecimal okay, which is base 16. So rather than base 10, which is most of our work was being done, we are now going to be using hexadecimal, which is base 16, and the numbers are labeled hexadecimal bits, decimal, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, not 10, A, B, C, D, E, and F. Okay, so their bits are 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, and 1, 1, 1, 1. So in decimals, these are going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, sorry, starting from 0. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and a 15. Okay. And how do we show that something is written in hexadecimal? Generally, denote hexadecimal by OX, 0x, not OX, 0x at the start. Okay, so for example, 0x 10 is equal to 16 into 1 plus 0 into 0 as well, plus 0. So that is just 16, which is the code for, well, that is literally, that is its own code. Okay, so in terms of bits, this is going to be 0, 0, 0, 1, 0, 0, 0, 0, right? That's the code for 1, 0. The code for 0, 0xAF is then, well, this is 16 into A plus F, which in decimals is, well, A is 10, so this is 16 into 10, and F is 15, so this is 175. In terms of bits, this is 1010 plus 1111. Not plus, just 1010 1111. You're saving it into different bits. So each bit is of length 8. So generally, all of such messages are, this is used to code messages in ASCII. Used to code messages in ASCII. C-I-I. Okay, so in ASCII, we have some message, and I'm not going to give you the entire chart of what the letters are coded as in ASCII, but 0 cross 4 1, 0 cross 4 1 is equal to letter A, capital A, okay? Then it goes down, so 0 cross capital Z is 0 cross 5A is equal to letter capital Z, okay? 0 cross 6 1 is letter small a, and again dot dot dot, 0 cross 7a is equal to letter small z. Okay, so assuming I am using lowercase messages, assuming the message is in lowercase English, we first encode it into a code, okay, and we use that code. Use the letters will begin from 0x6 or 0x7. Okay. So there are two ciphers that we are going to look at. First is bitwise shift cipher, bitwise shift cipher, and then modified bitwise shift cipher with a combination of Ignera cipher. So let the message space M is equal to string of bytes, okay? So each letter is going to be some ASCII character that has a string associated, that has a byte associated with it, okay? So that has 2 bytes associated with it. It would be 2 4-digit blocks associated with it, okay? So my message space is the string of bytes. My generator, key generation algorithm, chooses a uniform byte. Choose uniform byte k in the space, key space, which is 0 to 255, which, if you think about it, is equal to z 16 squared, right? That's because each byte is of the is of 4 binary letters. 2 to the 4 is 16, and we are using 2 4-byte strings. 2 bytes. Each byte is actually 8, so that's the string. 8 bits is a byte. My bad. So I'm using 1 full byte, which is 8 bits, and 2 to the 8 is 256. So 2 to the 8. Okay. Then the encryption using this key of the message M1, M2 dot 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 MT gives the output output C1, C2, CT, where CI is equal to MI XOR K, bitwise sum K. So this is bitwise sum. I will show you an example in case you're not familiar what that means. Bitwise sum. Okay, so this is sum in the base 2. 1 plus 1 is 0, 0 plus 1 is 1. Okay, and you just add the bits. And then the decryption of this key, decryption of C1 CT is actually just, you want it to be your exact message that you started with, M1 MT, but how do you get it? Where MI is actually just CI sum K. You just use modular sum again and it cancels out. Okay, now example. Okay, before we get to an example, let me just say this. Is this secure? Is this secure? The answer is no. No. Only 256 possible keys. Only 256 possible keys. So even a brute force algorithm is going to just render this encryption useless pretty fast. And so what we do is, to complicate it, we do slightly better. What we do is we combine it with the Vignera cipher. Okay? Actually, do I want to do that example? Okay, I won't modify it with the Vignera cipher. I will just show an example of the normal cipher. So example. So suppose my message text is plain text. Plain text is, say, hello. Okay, that's my plain text. And my key is 0 cross 0x A1 to F. Okay, so A1 to F is a complete byte. A1 is the first 4 bits, 2F is the second 4 bits. Okay, and the plain text hello in when converted to ASCII and when then converted to hexadecimal is actually 0 cross 48, 65, 6C, 6C, 6F, and 21, where 21 is the exclamation point. Okay? And so I am going to encode it with 0x A1 to F to F. I'm sorry, A1 to F, A1 to F, A1 to F, A1 to F. Okay? And now, how does the addition work? Okay? So XOR how does XOR work? XOR of 0 cross 4 8 and 0 cross 4 1 A1 0 cross A1 is equal to 0 cross 4 8 some 0 cross A1, which is equal to 0 1 0 0 1 0 0 0, which is the key for 8, XOR 1 0 1 0 0 0 0 1. And XOR now is just bitwise comparison. Last bit of both is 0 plus 1, so this becomes a 1. 0 plus 0, that stays 0. 0 plus 0 stays a 0. 0 plus 1 becomes a 1. 0 0 stays 0. 1 0 becomes 1. 0 1 becomes 1. 1 0 becomes 1. If any of them were both 1s, if this was, for example, 1 1 1 1, then this would have become a 0 rather than 1. There is no carry forward. There is no method of carry forward. It would have just become 0. Okay? But this is the code, which is the code for 0 cross E9. Okay? And so that is the XOR for the first two. Similarly, you do the entire process and you get ciphertext as 0 cross E9 for A, CD for 3, CE 0E. Okay, so that is my ciphertext, and you can do it by the decoding is going to be exactly the same. To decode, you just hit decryption, CRYPT, decryption, XOR with, again, the key, which is going to be 0 cross, what was my key again? A1F2? A12F. A12F, which is to say I would have E9 for A, CD for 3, CE 0E XORed with, so let me just write plus A1 2F A1 2F A1 2F, and let us verify if that does indeed give me the correct thing. So 0 cross E9 0 cross E9 direct sum XOR 0 cross A1 is equal to, well, the key for E9 is 1 1 1 0 1 0 0 1, and I am adding to it A1. A is 10, which is 1 0 1 0, and 1 is 0 0 0 1. Bitwise sum 1 plus 1 0, 0 plus 0 0, 0 plus 0 0, 1 plus 0 0 1. 0 plus 0, 0, 1 plus 0, 1 plus 1, 0, 0 plus 1, 1, 1 plus 1, 0, which is exactly equal to 4, 8. 0 cross 4, 8, right? And so I would be able to decrypt my original message. So this is the bitwise shift cipher. Bytewise shift cipher. How do you do bytewise Vignera cipher? Well, you use more than one byte. You just use 2 bytes or 3 bytes or 4 bytes, combine them, get a string of large size, and produce bytewise Vignera cipher. Vignera cipher. Take of L bytes, LB bytes, and just do the same process as shift bytewise shift cipher. It's called bytewise or bitwise? Bitwise shift cipher. Bitwise shift cipher. Okay. So these are some of the examples of a classical ciphers. Okay. And now we will want to know what exactly is that we are going towards. These are all perfectly fine ciphers, but are they secure? What does it mean by something being secure? Okay, and for that we need certain things. We need to be able to define what it means by something to be secure, first of all, to say, oh, this is secure or this is not secure. So basic principles of modern cryptography. Basic principles of modern cryptography. So most of what we saw till now was completely classical cryptography. To go to modern cryptography, we need to properly define things. Okay, so here are the 3 principles that we are going to look at. First, principle 1. The first step in solving any cryptographic problem, the first step in solving a cryptographic problem, is the formulation of a rigorous and precise definition, of a rigorous and precise definition of security. We cannot say if something is secure or not if we don't know what it means to be secure. Second principle, when the security of a cryptographic construction relies on an unproven assumption, unproven on an unproven assumption, this assumption must be precisely stated. This assumption must be precisely stated. Furthermore, the assumption should be as minimal as possible. Furthermore, the assumption should be as minimal as possible. As possible. Why do we want it to be as minimal as possible? The bigger the assumption, the harder it becomes, the easier it is to fail. If you're using it for a very, very small thing, there's a higher chance that even if the assumption does not work, your system is still going to work. Okay? So you want to use unproven assumptions as little as possible and while stating it as precisely as possible. And third, cryptographic system constructions. Graphic constructions should be accompanied with a rigorous proof of security. Should be accompanied with a rigorous proof of security with GROUS, rigorous proof of security. With respect to a definition, definition formulated according to principle 1. Formulated according to principle 1. Principle 1 and relative to assumptions and relative to assumptions in principle 2. Okay, so these are the assumptions that we are these are the principles that we are going to base our system of modern cryptography for. And what is the need for each of these? Why do we need these assumptions? So I'm going to briefly discuss these. I'm not going to go into complete details because I expect you to read these parts, but we need precise definitions for importance in design so that we can understand what we are doing. Okay, we can't say, oh, this is how we are, this is exactly, it is so good, without saying why it is good. And yeah, and you cannot tell someone, oh, use this system, it is more secure, without having them having some idea of what it means for it to be secure, and B, without you being able to explain to them what it means for a system to be more secure. Okay, so the definition that we are going to for now use, definition of secure that we are going to for now use is that an encryption is secure if no adversary can compute any function of the plain text can compute any function of the plain text from the ciphertext from the ciphertext i.e. what does that exactly mean? What does it mean by any function of the plain text? Well, it means they should not gain, i.e. they should not gain any new information about the ciphertext than what they already have. The plain text and its use than they already have. Okay. However, this is a very informal definition. So let me just say informal. I don't know how much or what is the what exactly I mean by function of the plain text from the ciphertext. We will look at that in the next video in chapter 2. Okay, so I will stop this one right here.